Every nuclei that's associated with a nuclear spin quantum number I has a magnetic moment that is associated with. Each of these are vector quantities, and the magnetic moment for a given nuclei is proportional to its spin quantum number. And it's related to the spin quantum number with a constant which is called the gyromagnetic ratio. This is also referred to as magnetogyric ratio, as this is a ratio of the magnetic moment to that of its angular momentum. As anything that gyrates is associated with the angular momentum, the gyromagnetic ratio also comes up for nuclei that have a spin. The strength of the magnetic dipole moment that is present is dependent not only upon the spin quantum number but also on the gyromagnetic ratio. Let's take a look at gyromagnetic ratios of some spin half systems. This will be easy for us to compare, largely because the magnetic moment will only then depend upon the gyromagnetic ratio. The gyromagnetic ratio is given in units of radian per Tesla per second. So proton has a magnetogyric ratio of 27.6522 into 10 to the power of 7. And 13C has 6.7283 into 10 power 7. 15N interestingly has a negative sign in front of it, minus 2.7126. And 31P has 10.8394. Fluorine F19 has 25.1815. The important thing that the magnitude of the gyromagnetic ratio makes us understand the dipole moment that comes up for each of these nuclei, although all of them are spin half, is going to be different. And most importantly, proton having the highest of gyromagnetic ratios is going to have the highest of dipole moments. I'll try to draw this but not to scale. So let's assume proton has something as long as this. So let's say this is 100 units. Fluorine will have something close to 94 units, followed by phosphorus, which is going to be something of the sort of 41 units. And this will be followed by carbon, which will be close to 25 units. How am I calculating it? If you take the ratio of the gyromagnetic ratio of carbon to proton, you get 1/4. So if you scale proton to 100, you get 25 for the carbon. And nitrogen will somewhere be like 1/10. So you're going to talk about 10 units. And remember, since nitrogen has a negative gyromagnetic ratio, the vector is not going to be pointing in the same direction. It would rather be pointing in the opposite direction. So therefore, one is able to understand when you have a non-zero nuclear spin quantum number, is a magnetic moment that is associated with it, whose length is based on both the spin quantum number and also the gyromagnetic ratio. In this course, most often we will be focusing on spin half nuclei only. NMR, as I said, can be done for any nuclei that has a spin quantum number that is greater than 0. Since some of the properties for spin quantum number greater than half is not desirable, it is little difficult to do NMR of spins that are greater than half. These spins are also called as quadrupolar spins, and one ends up doing NQR with them, nuclear quadrupolar resonance spectroscopy. Since, as I said, magnetic resonance is what we'll be focusing on, we'll be more focusing on the spin-half nuclei for the entirety of this course. Whenever required, we'll be invoking some of the aspects that might be required for us to understand. Otherwise, we'll be pertaining ourselves to spin-half systems only. For every spin quantum number that's associated with I, you have states that go from minus I to plus I in integer steps of 1. This is very similar to what you would have seen in the rigid rotor model, where you have the L quantum number that is dictated by the principal quantum number n, and the ml quantum number is dictated by L that goes from minus L to plus L in integer steps of 1. Since the nuclear spin quantum number can be half integral, let's take this example of half. The mi in this case will be minus half plus 1, which will be plus half, and of course it cannot go higher or lower than that of the quantum number itself, so we are restricted to these two quantum numbers. So in this case, you are going to have two energy states that are going to be degenerate in the absence of any fields that are applied. But the moment you apply a magnetic field, what ends up happening is that these two states that were previously degenerate end up splitting from one another. This is largely because energy for a magnetic dipole is given by minus mu dot B, where mu is the magnetic dipole moment, which we just saw a moment back how it behaves for a nuclear spin, and this is the magnetic field that is applied. In the field of NMR spectroscopy, we would be referring to the magnetic field that is applied as external magnetic field B0, and we will take the direction of application of this field along the z-axis. If you would like to know why, you might remember the representation of the angular momentum operator is the simplest along Lz, in this case Iz. And mu, as I said, is going to be given by product of gyromagnetic ratio, which is a constant, followed by the I vector. And I is going to be given by Ix times I plus Iy times j plus Iz times k. And for every observable in classical mechanics, it's observed with a quantum mechanical operator, so that is going to be the Hamiltonian we are talking about. And the mu, of course, I'm changing it to I already, it's going to be I cap dot B cap. Since the dot product will result only in the k terms surviving, you are going to get something like minus gamma B naught times Iz. The two states that we have generated here can be represented as the I quantum number, comma, Mi. When we operate Iz on this state, you are going to end up getting m h cross, in this case m is half, so you are going to get half h cross back the function, because we know these are eigenfunctions of the operator Iz. And when you operate Iz on half comma minus half, which is the other state, you end up getting minus h cross by 2 and the state back. Let us take a look at the energy of these two systems. Before I get there, I would like to define a few more things so as to make our writing easier. The half comma half state is generally referred to the alpha state, and the half comma minus half state is referred to the beta state. So the same thing can be rewritten as Iz on alpha is going to be half times alpha, where h cross is set to 1, and Iz on beta is going to be minus half times beta. When we look at the energy equation, the plus half state will be associated with energy which is going to be minus gamma B naught by 2, and the beta state is going to be associated with plus gamma B naught by 2. So let's write it again. E of alpha is going to be minus gamma B naught by 2, and E of beta is going to be plus gamma B naught by 2. Since we just saw a bunch of examples where gamma greater than 0 is the most common, of course, except 15N, which is a spin half nuclei. The two degenerate states, when a B naught is applied along the z-axis, end up splitting, with the alpha state being the ground state and the beta state being the excited state. And the moment you have an energy separation, you can actually interrogate these systems with the EM wave. And as I had mentioned, NMR ends up using RF radio frequency pulses. So when you apply radio frequency pulses and receive them back, you will be able to understand what is the energy separation that ends up coming. So therefore the delta E between these two states is the energy of alpha minus that of beta. So minus gamma B naught by 2 minus plus gamma B naught by 2, which will end up being minus gamma B naught. And this will be from here on referred to as omega naught, and this is what is called Larmor precession frequency. This is characteristic for a given nuclei that you end up looking at because of the gamma being present. So let's take an example. From the case of proton, which has a magnetogyric ratio of 26.6522 into 10 to the power 7 radian per Tesla per second. If you apply a B naught of 11.74 Tesla, your omega naught is going to be the product of these. NMR spectroscopists always like to refer this the unit of frequency, so therefore we have to divide by 2 pi in order to account for the radian. You will observe that this value comes to 499.859 into 10 to the power of 6 hertz. I had made a small mistake here. Please note this value is not correct. This is 26.7522. That will result in this value. And one is able to understand you have a 10 power 6 term that comes up. So generally you would refer to 11.74 Tesla magnet in NMR to something like 500 megahertz. The exercise for you is to find what will be the B naught when you refer to 300, 400, 600, 700, 800 and 1000 megahertz. The other assignment that I give you, what is the magnetic field of the earth? Basically, what's Earth's magnetic field? So find it so that you understand what is the magnitude of the magnetic fields that we end up using in NMR spectroscopy. Let me reiterate a little bit. You have two energy levels that are degenerate. On application of B naught, you end up having splitting of these energy states, which is given by minus gamma B naught, and which is what we call as the Larmor precession frequency. And this precession frequency depends upon the gyromagnetic ratio. The population difference between these two states, P alpha minus P beta, is what relates to the sensitivity of this given experiment. Meaning that more is the difference in population, you would say that the spectroscopy is a sensitive technique. On the other hand, we started with the premise that NMR is an insensitive technique. We will take a look at why this is indeed the case. So let's take a look at what is the fraction of molecules that will be present with the state alpha. That is going to be given by the Boltzmann's distribution, which is going to be given by e power minus delta E by kBt, where kb is the Boltzmann's constant, divided by e power minus E alpha by kBt plus e power minus E beta by kBt. The delta E is given by minus gamma B naught. E alpha is minus gamma B naught by 2. E beta is plus gamma B naught by 2. Why don't we take a close look at what do we get as delta E by kBt. This is going to be equal to gamma minus gamma B naught, since minus and minus gets cancelled. So I'm going to write minus delta E by kBt is going to be this given value. If you take a moment to calculate this, you have to be, however, careful here, because for the sake of simplicity, in the previous portions we had set h bar is equal to 1. However, for this calculation you have to include it explicitly in order to understand what we get. So let us calculate this. 26.10 to the power of 7 radian per Tesla per second times 11.74 Tesla times 1.05 into 10 power minus 34, the whole divided by 1.38 into 10 to the power of minus 23 joule per Kelvin times, let's try to do this at 298 Kelvin. We understand here that the Tesla and Tesla cancel with each other, per second and second cancels with each other, and radian will cancel with each other as well. The denominator per Kelvin gets cancelled. Finally, you have a joule by joule, which makes this entire term unitless, equal to 0.80 into 10 to the power of minus 4. Whenever you have functions such as e power x, this can be expressed as a Taylor series expansion of 1 plus x squared by 2 factorial plus x cubed by 3 factorial and so on until infinity. Since the value of x is much less than 1, one can actually approximate this to 1 plus x. The term that we end up looking here is going to get further simplified. N alpha by n will therefore become 1 minus of minus will be plus gamma b naught by kbt, the whole divided by 1 plus gamma b naught by 2 kbt plus 1 minus gamma b naught by 2 kbt. These two terms will cancel with each other. These two will add up to give you 2. So therefore, this ends up being 1 over 2 times 1 plus 0.8 into 10 to the power of minus 4. So therefore, the population in N alpha with respect to the total population is going to be 1.00000 plus 0.00008 divided by 2. This is going to be equal to 1.00008 divided by 2. That is going to be 0.50004, implying the N alpha state has about 50.004% population, and the N beta is going to be 1 minus of this, 49.996%. We can actually write them as P alpha and P beta. Therefore, the delta P, which is the population difference of P alpha minus P beta, is going to be 0.008%. We clearly see there's a very small population excess in the alpha state. This results in the fact that NMR is an insensitive technique, meaning that you need to have a large enough concentration in order for this 0.008% to matter. Of course, in this example, we took that B naught is 11.74 Tesla. Let's say if you are able to go to something like 23 Tesla, which will be close to 1 gigahertz, you'll still be able to increase the population, but not by very much. You're going to increase it in this decimal. So therefore, it is apparent that only if you have large enough concentration and a good enough magnetic field strength, this small population excess would help you get signal that is discernible from noise that is already present. One might be curious of the fact, in addition to B naught and gamma that are present, this equation is also dependent upon temperature. What will happen if you reduce temperature from 298, which we ended up using in this example? You would realize that instead of dividing the whole equation by 300 Kelvin, which we used as 298, even if you divide it by 1 Kelvin, which is reducing it by 2 orders of magnitude, you would end up changing this to not very much. And remember, once you start cooling systems too much, you would end up going from solution state to solid state, which might not be what you want to do for the system that you're trying to look at. This approximation that we ended up exploiting here, where gamma B naught is much less than kBt, is called the high temperature approximation. And this almost holds good for most of the systems that we will end up looking in this class. In addition, you also have the gamma that goes into here. We calculated this ratio for proton, which ends up giving you a percentage excess of 0.008. If you end up applying this for the carbon, you're going to have 1/4 of this, which means that it's going to be much lesser. On the other hand, if you end up applying for phosphorus, it's going to be close to 40% of what you get for proton. Similarly, for fluorine, you end up getting something close to 94% of that of proton. Immediately you are able to understand that NMR is the most sensitive for proton, followed by fluorine, followed by carbon, followed by nitrogen, in that order. Phosphorus will fall somewhere between fluorine and carbon. So the gamma ends up dictating which nuclei end up being sensitive, which is why almost always synthetic chemists end up getting a proton NMR followed by carbon NMR. If they have to do any other nuclei, they end up looking at what is the gyromagnetic ratio and what field strength works the best for them.